Hello, everyone, and welcome to Physics 212. This is Lab 10, which is the second experiment on the work energy theorem. So in this lab, we're going to use the Pasco car to do several experiments where we look at work and energy, and we also look at conservation of mechanical energy. So again, the video that's going to follow is a video that I originally recorded during the pandemic. However, the questions from your lab manual are exactly the same. In this particular video, they actually match up exactly. The numbering matches up as well. The only thing that you'll notice is that some of the data, again, is collected for you because this was a pandemic. We couldn't collect data. So if you are watching this video because you need to make up Lab 10, you can either use the data that's already in the tables, that would be fine, or you can get the current data from your lab partners from this semester, and that will be fine as well. Okay, great. So now let me transition to the original video that I recorded a year ago during the pandemic. All right, so that's it for part one. For part two, so this is sort of another way of looking at the work energy theorem. In this case, what we did was we used these Pasco dynamics cars, these Pasco cars that have like wheels, but they have really low friction in their wheels. So you can kind of think of it as almost being frictionless again, all right? So to get a good idea of how I collected this data, please make sure you watch this short video on how I collected the data for this first part of this, of part two, the experiment. Basically, if you look at this, right, here's a picture. We have the Pasco car. It's going to start at a position of 20 centimeters. There's a string connected to it. It goes over a pulley, and there's a little suspended mass here. This little gray. Actually, you can see better in this picture. So here's a suspended mass. It starts at rest. We release the car. It's going to accelerate down the track. It's just a horizontal track now. And it's going to travel undergo a displacement of 0.6 meters, right? So it's going from 20 centimeters to 80 centimeters. That's 60 centimeters, which is 0.6 meters. And ultimately, what we want to do is we want to calculate the work done by the net force as it undergoes that displacement of 0.6 meters. Okay, so let me describe this system, and I'll do this on the iPad. Okay, so in this case, right, we have the flat horizontal track like this. We have the Pasco car right, on the track, and then there's a pulley here. A suspended mass. And when we release the car, it's going to accelerate down the track, okay? So what is the system in this case? Well, the system that we're going to consider is, again, just the car, right? The car on that flat track. So this is going to be our system, just a car. Well, what are the forces acting on that car? Well, we have the weight again, right? So that acts towards the center of the earth, right downwards. We have a normal force that the track exerts on the car. Normally you would have friction, but again, we're assuming that the bearings and the wheels of those cars are very good, so it's basically frictionless. So the only other force we have, since we have a string connected to the car itself, we have a tension in the string, which is pulling on the car to the right. So a tension to the right. So if we look at our general work energy equation, right, the net work done is equal to change in kinetic plus change in gravitational potential plus change in elastic potential or spring energy, thermal energy, etc. again, we can eliminate almost all these things, right? We're assuming there's no friction, so we have no change in thermal energy. We're assuming there's no spring or anything in here, so no change in elastic potential energy. It's not going up or down the track, right? And plus, we're just considering the car by itself, so there's no change in gravitational potential energy. So again, we can say that the net work done has to equal the change in kinetic energy. So that's similar to before. So in this case, the net work done is going to be equal to 1/2 mv final squared minus 1/2 mv initial squared. Okay, so let me go back to the handout. Okay, so if you look at the tables, this is sort of the main data table for this part. So in every trial, there's like 5 trials here. In every trial, the car started at 0.2 meters and ended at 0.8 meters. So its displacement was simply the final position minus the initial, x2 minus x1, which is 0.6, right? So the displacement is 0.6 meters. This delta T12, that's the total time it took to travel that 0.6 meters. So if you go back to the picture here, basically you release it right before it triggers the first photo gate, it accelerates down and it triggers the second photo gate, and it gives me the time between those 2 photo gates, right? So it's the time for it to travel the 0.6 meters. So that's where this data is coming from. So these values are the time to travel the entire 0.6 meters. The initial velocity of the car was 0 because it started at rest, right? And we need to figure out the final velocity when it passes that second photo gate, right? The one that's at 0.6 meters away. So how do we figure that out? Well, what I did was I found the time it took. So this delta T here is the time it took the flag, which is really just like a metal post, to pass through that second photo gate. So this is kind of like, do you remember when we did the ball drop experiment? If we want to know the velocity at a photo gate, it was like the diameter of the ball divided by the time it took to pass through. Well, in this case, it's going to be the diameter of that flag divided by delta T, the time it took to pass through, and that will be your final velocity. Okay, so basically in the picture here, when the car accelerates down, I want to know the final velocity right at that instant. So I took that flag length divided by the time it took to pass through, and that should give me a good estimate of that final velocity. Okay, so the first question, I want you to compute that final velocity. So it's going to be the flag length, which I give you here, divided by this time. So compute that final velocity, and then compute the average, and maybe show me like a sample calculation. Then I want you to compute the acceleration, right? This is really the formula for the average acceleration, but we know the acceleration is constant as it accelerates down that flat track. So the acceleration is simply going to be the change in velocity over the change in time. So it'll be v2 minus 0, right? Minus v1, which is 0. And then divided by the time, and the time it takes to travel was the time it takes to travel that entire 0.6 meters, right? So it'll be this time right here. So you're going to compute the acceleration and then find the average acceleration. Okay, you need the mass of the car. So I have that in the table here. This is in kilograms, right? Everything is in SI units today. The acceleration is, you just computed it, this average, that's the same value that goes here, average acceleration. Now using Newton's second law, you can compute the net force acting on that car. And actually, what is the net force? It's really just the tension in the string, right? Because the normal force and the weight are going to add to 0. So the only force remaining is the tension in that string. Right, so that's going to be the net force in newtons, right? You're just going to use ma, mass times acceleration, to get that net force. Okay, once you have that net force, right, and we know the displacement, that's 0.6, and we know the angle between those two values, since the net force is simply going to be the tension The displacement is along the track. So the angle between those two is 0 degrees. So really this should have times cosine of the angle, but cosine of 0 is equal to 1. So the net force is simply equal to the net force. Sorry, the net work is simply equal to the net force times the displacement, right? Times 1. So that'll go here, the work done by the net force, and the units are joules. Then, since we know the final velocity, calling it v2 here, we know the mass, we know the initial velocity, right? It starts at rest, so it's 0. So you can compute the change in kinetic energy. So that value will go here. Make sure you show me these calculations for the net work and the change in kinetic energy. And then finally, I want you to compare these two, right? By computing what's called a percent difference. It's really the same as a percent experimental error, except that we're deciding that the net work is going to be like our accepted value, okay? But it's really nothing more than a percent experimental error. We're just calling it a percent difference here, right? Because there's truly not something that is really accepted, the accepted value. And what should we get? Well, think about the work energy theorem, right? We know that the net work done should equal the change in kinetic energy. So if I compare these two, hopefully I get a very small value here, right? It should be, in theory, it should be equal to 0. It won't be exactly 0, but hopefully it'll be a fairly small value. Okay, so that's it. So that's it for part 2. Part 3, now we're going to look at something called conservation of mechanical energy. So let me go back to the iPad and explain this part. Okay, so in this part of the lab, we have the Pasco cars, and they're going to be like launched up an incline track. And in this case, let me draw a car here. We again have two forces acting, right? We have the weight of that car, and we have the normal force. But in this case, for our system, we're going to include the car and the earth as our system. So car and earth. So let's say, this is like the earth. So the system is going to be the car and the entire earth as our system. Now, this is a subtle point, but what this does is it allows me, instead of looking at the work done by the weight, right, the gravitational force, I can consider that as a change in potential energy instead, right? It's a subtle point. It's something that you guys will get into more detail in lecture, okay? So for now, think of it like this. If we look at our general work energy theorem, so I have the net work done is equal to change in kinetic plus change in gravitational potential plus change in elastic potential plus change in thermal plus ... Okay, again, we're assuming there's no friction. We're assuming there is a spring actually that's used to launch the cart, but once it leaves the spring, there's no more energy due to the spring, so we're not going to consider that. So we assume that is 0. But because it's going up an incline, it's changing its height, and for our system, we're including both the car and the earth, then I do have a change in potential energy, okay? And it turns out it's equal to, or it's related to the work done by the weight vector. Now, there's only another force there, right? There's only the normal force. And since the displacement is up, the displacement is sort of in this direction, that normal force is not going to do any work, right? Because the angle that the normal force vector makes with the displacement vector, this is really a vector, is going to be 90 degrees, right? And cosine of 90 is 0. So the normal force does no work. So the only thing that does work is the weight, but that's going to be included in this term when we look at the change in gravitational potential energy. Again, it's a very subtle point. You will learn more details about this in lecture. So what's going on in this example is there is no network, there's no other forces acting, right? So the net work done is going to be 0. So this is going to simplify to the following. It'll be 0 is equal to the change in kinetic energy plus the change in gravitational potential energy. Okay, but we know the change in kinetic is 1/2 mv final squared minus 1/2 mv initial squared. We know the change in gravitational potential is going to be mg, I'll call it y final, minus mg y initial. Typically what people do is now they move the initial terms to the left-hand side. So if I add, right, if I add these two terms, I'll write this one more time. Let me add these two terms that contain the initial velocity and initial height to both sides. So what I'm going to get for final result is on the left-hand side, I'm going to have 1/2 mv initial squared plus mg y initial. That's going to equal, on the right-hand side, I have 1/2 mv final squared plus mg y final. So basically what I'm saying is that my initial kinetic energy, I'll call it Ke for this time, plus my initial potential, I'll just call it Pe instead of U. So Pe initial, that's got to equal my final kinetic energy plus my final potential energy. And the sum of kinetic and potential is what we call mechanical energy. So really what I'm saying is that mechanical energy initial is equal to the mechanical energy final. So this is a situation where the mechanical energy should be conserved, right? The initial value equals the final value. So mechanical energy is conserved. And typically if there's no like frictional forces or something that's dissipating energy, or, you know, energy is being put into the system, typically mechanical energy is going to be conserved. Okay, so let me go back to a little handout. Okay, so again, make sure you watch that short little video, right? I show you how I actually collected the data. So here's the car, right? Here's the first photo gate. The second photo gate you don't even need. You can ignore the second one. We really only need the first photo gate for this part. What we do is we compress the spring. There's a little spring on the car here. And then we release the car, right? It's going to have some initial velocity. And we can calculate that initial velocity because we will know the time it takes that little flag to pass through the photo gate. So if I do the diameter of the flag divided by the time it takes to pass through, that's going to be my initial velocity, right? The initial launch velocity of the car. And then it's going to travel up this incline ramp. And at some point, it's going to be, just for an instant, its velocity will be 0, right? It's going to stop for an instant when it reaches its highest point. So what's going on here? Basically, there's some potential energy initial, right? Because I'm going to call the table my reference point. So if I measure the height from the table to, let's say, this little sticker on the car, that's going to be my initial height. So if I do mg times that initial height, that's going to be my initial potential energy. Since the car has some velocity initially, right? The spring gave it some initial velocity. We're going to measure that velocity. then we know it has initially a kinetic energy, right? It'll be 1/2 times the mass of the cart times that initial velocity squared. So it has an initial potential energy, it has initial kinetic energy. When it reaches the highest point, it definitely has a potential energy. In fact, the potential energy is larger now, right? Because the y final is greater than y initial. So remember, it's mg times y final. But the kinetic energy is going to be 0 because the velocity is 0, right? For an instant, it's at rest once it reaches its highest point. So throughout this entire motion, we're saying mechanical energy is conserved. So if I sum the potential energy plus the mechanical at the first point, it's got to be equal to the potential energy plus the kinetic at the second point. I said it backwards, sorry. The mechanical energy is kinetic energy plus potential energy. So if I sum the potential energy plus kinetic energy at the first point, that's got to equal the sum of the potential energy and kinetic energy at the second point. In fact, it's got to equal to the sum of the potential energy and kinetic energy of the car at any point throughout the motion, right? Because it's conserved, it's equal to a constant throughout. So what's happening here is that the car is gaining potential energy, but losing kinetic energy, right? Because it's slowing down. So its kinetic energy becomes less and less and less and less, but the potential energy becomes greater and greater and greater. And the sum of those two is always going to be a constant, which is equal to the mechanical energy. Okay, so in terms of your lab report, here's what you need to do. So I measured the initial height. So y1 is the initial height. This is in meters. And then when it reached the highest point, when the cart launched up, reached the highest point, I measured it there as well. This is the highest point, 0.160 meters. And we also are going to need the mass of the cart at some point. Okay, remember at the beginning, right? Once it's launched from the spring, right when so it passes through the initial photo gate, I want to know that initial velocity. So how do I find that? Well, it's going to be the flag length. So the diameter that it's like a metal post actually that's on the car divided by this time. This was the time it took that post, that metal post, to pass through the photo gate. So first question, 16, compute that initial velocity for all 5 trials and find the average. Then I want you to compute the mechanical energy of the car at position 1. So you have to compute the initial kinetic energy and the initial potential energy and add them together. And that'll be the initial mechanical energy. Question 17, compute the mechanical energy of the car at position 2. Remember, it's instantaneously at rest. Really, rest is not the best way to say it. It's instantaneously has a velocity of 0, right, at that point. So what is the kinetic energy at position 2? It should be 0, right? So the mechanical energy at position 2 is all going to be potential energy. So you would, if you compute this potential energy, that should be the mechanical energy at position 2. Then you want to compare these two values. So compare the mechanical energy at position 1 with the mechanical energy at position 2 by computing. We're going to call it a percent difference again, because it's not clear which one really should be our accepted, right? So we're just going to choose to divide by mechanical energy at position 1. So this is the mechanical energy at position 1 that you got from question 16. This will be the mechanical energy at position 2 from question 17. And then finally, you're going to compute this percent difference, which is just like a percent experimental error, but we're going to choose to put mechanical energy at position 1 as our sort of our accepted, right? So, and make sure you show me all these calculations. And then simply last question, were you able to successfully verify the law of conservation of mechanical energy? Given that it's an experiment, there's going to be some error, right? It's really hard to figure out exactly how far up that car goes, like when it is actually at rest. There may really be some friction, right? There could be a little bit of friction there. Those wheels aren't perfect. So there are a few reasons why you may not have obtained the same exact mechanical energy values. But in theory, if there was no friction, no air resistance, you have exact measurements, these two values should be exactly the same. Okay, so hopefully they're fairly close. All right, that's it. So that was our lab on the work energy theorem, and we also looked at conservation of mechanical energy. Great, thank you.